Bicopter. So we'll first talk about modeling a bicopter, and I'll show you what a bicopter is, and then we'll do some control with it. So a bicopter is essentially a 2D version of a quadcopter. So a model for a bicopter would be something like this. The base is the center of mass, and there are two propellers. So so these propellers are basically motors which spin the propellers, and the goal of spinning the motors is that they generate a thrust, and the thrust is always pointing in the direction, depending on the direction, of course, of the motors. You will have the thrust upward or downward. In this case, let's assume that the thrust is upwards. There is gravity, which these propellers have to fight so that the bicopter is balanced. Let's put xy to be the location of the base. Let's say that the mass is m, inertia is I. So this is the inertia of the entire system. Assumed it to be at this midpoint, and let's give it some length. This is the distance between the attachment points of the two propellers. Okay. And then we need one more variable before we can think about modeling this. There's a angle which the base makes, or the bicopter makes with the horizontal. Let's say it's phi. Okay, so far what we have described here is mi, the mass, inertia, g and l. G is gravity, and L is the distance between the propellers. U1, U2 are the thrust forces. And we have X, Y, phi are the degrees of freedom. In other words, these are the things you need in order to describe the motion of the bicopter. Okay, so without the equations, we cannot do control. So let's think about deriving the equations of motion. Okay, we'll use the method we've learned so far, Euler-Lagrange method. So here are the key steps. I'll just follow those steps in order to derive the equations. So first step was get the positions, velocities of the center of mass. Here we are fortunate that we don't really need to do much work here. X, Y, theta are the positions, and X dot, Y dot, sorry, this should be phi. Phi dot are the velocities. So that is fairly straightforward here. Okay. The second step is get or compute the kinetic and potential energy. Now that is also kind of straightforward. T is the kinetic energy. It's half mv square, v being the velocity, the linear velocity of the center of mass. So the velocity of the center of mass will simply be x dot square plus y dot square. Okay, but that's only the energy associated with translation. There is another piece associated with uh, rotational motion, that's half I omega square. Omega here is phi dot, and so phi dot square. The potential energy is simply mgy, and then the Lagrange is t minus v. Okay, so far so good. It's fairly straightforward. Okay, now, one thing we need here, which I think is the hardest part of this, is not really hard, but it's really required some work, is the thrust forces U1 and U2 provide thrust to the bicopter, and we need to figure out how those thrust forces come out as generalized forces on the bicopter. By generalized forces, I mean in the Euler-Lagrange equations, you will have an equation which will be some calculus terms equals capital Qj. Those Qj's should be the force in the x, y, and phi direction. So let's do that. But let me write this down why we're doing it. So in Euler-Lagrange, we need to compute generalized forces Qj, right? So you can recap that the equations are d dt dl dqj dot minus dl dq j equals qj. So this is the generalized force, and we need a force in the x direction, we need the force in the y direction, and we need the force in the, or the torque in the phi direction. So those four, or those three forces, those two forces, linear forces and one torque, are the ones which we need, and those come because of U1 and U2. So see U1 and U2. U1 and U2 is producing a force in the vertically up direction of the current orientation of the bicopter, but we want the force in the y, x, and the phi direction. So x, y, and phi. So clearly we could do this by trigonometry, right? You could take U1, resolve it along y, resolve it along x. You could also find the moment due to, or the couple due to, moment is the right word, moment due to U1 and U2. So that's one way of doing it, which we've not really done in this course. The way we've done the forces is we've used the homogeneous matrix in order to do that. So let's use the homogeneous matrix to figure out the forces. Okay, so let's do that. Okay, so for that, so that's the third step. Compute Qj. Okay, for that, I'll draw a figure. Okay, of the quadcopter. Let's assume that I draw. Yeah. Okay. And let's say that this point is P, this point is Q. I need to do the same thing I've done before, which is assign a frame. So let's say this is my base frame. I need to assign a frame along the direction of the base of the quadcopter. So let's say that this is going to be my second frame, x1, y1, and this point clearly is O1, O. No, actually, I'm going to remove that. Let's assume that it is actually floating somewhere, x0, y0. It doesn't have to be there. This is 0, 0. Okay. P. Yeah, I think that's all I need. Okay, so what is Qj? So Qj is nothing but, so remember there are two forces. There is force U1 and U2, and I want to compute what is the net force in the XYZ direction. So what I'm going to do is I'm going to use the Jacobian here to do it. Jacobian FP0 plus JQ transpose FQ0. We've seen this before. Okay, this is a way of computing the force at some point. So here it will be Q1, Q2, and then Q3 would be the rotational one. Okay, so I need to compute these four terms. Okay, so let's do that. In order to compute those terms, let's first. So what is Jacobian of P? It's basically dx capital X P d let's say Q, and this is dx Q dq. Or I think I should change my notation. It's going to be confusing. Let's call this R so that we are not stepping on the other variable we've used. So let's call this R, and then dxr dq. So this q here is x, y, phi, right? And xp and xr should be the positions with respect to frame 0. So xp would be the position of point p in frame 0, phi p in frame 0, and then orientation in frame 0. See, this should be, the dimensions of this would be 2 cross 1, because that will be the force in the x direction and the y direction. So this has to be 3 cross, so 2 cross 2 rows, 1 column. This should be 3 rows. J should be 3 rows, 2 columns. So that 3 times 2, 2 cross 1 is 3 cross 1. So my bad, this should just be xp, yp. And same for fr, xr. xr0, yr0. Okay, so this is just me thinking aloud what I need to do. Now is the process of just computing these 4 things. Okay, so let's do that. Okay, let's start off with something you've seen before, H10. This is the homogeneous matrix associated with the frame 1 with respect to frame 0. So this is just a formula which I've written down before. It's cosine phi minus sine phi, sine phi, cosine phi, 0, 0, and this 1. And this point should have coordinates of, maybe I should write it like this. Okay, hold on. Just rush to the substitution. Let me maybe write the first step. So H10 is R10, O10, 0, and 1, right? So I have R10 already over here. O10 is the position of this point with respect to frame 0. So that is just the XY coordinate. XY. That's it. Okay, now I need the location of point P in frame 0 because it's needed for the Jacobian. So I need xp0, yp0 to compute xp in frame 0, xr in frame 0. So in order to do that, I need p0. That would be h10 p1 cosine phi minus sine phi, sine phi, cosine phi 0, 0. Now position of x, y, 1. So position of p in frame 1. So it's this position. So remember that the length is L. This is L. So the position of P from this point, O10, is half of L. And that L is in the positive X direction. So L divided by 2, 0, and 1. So carrying out this multiplication will give you X plus 0.5 L cosine phi, Y plus 0.5 L sine phi, and then 1. Okay, similarly, if you want to compute R0, it's H10 R1. So H10 is the same as before. X, Y, 1. Okay, now we need the position of this point in frame 1. But you can see that this point here is along the negative x1 direction with a length of L divided by 2. So it'll be negative L divided by 2 along the x1 axis, 0 for the y1, and 1. So the carrying out the multiplication gives x minus 0.5 L cosine phi. So JP is dx p0 dq. So it's taking these terms, d dx xp0 dy d phi, and then repeat this for y, x dy p0 dy phi. Okay, we can do this kind of quite easily. So look at this equation. It is basically, this is the xp coordinate. So in order to take the derivative with respect to x, we see that the second term is constant with respect to x, so it'll just be 1, because it'll be dx, this dx gradient with respect to x. Okay, same thing with respect to y. Since there's no y term, this will be 0. And then phi, we'll see that this, you need to take the derivative of this part because it has a phi. That'll be minus 0.5 L sine phi. Next is yp, but this is yp. Okay, so that would be the derivative of this with respect to x. There's no x, so this is 0. Then derivative with respect to y, that would be 1. And then derivative with respect to phi will be 0.5 L cosine phi. Okay, so that gives JP. We had 4 things to solve for. We got one of those 4 things. So similarly, you'll see that this is XR0, and then this is YR0. So when we compute JR, we'll use those. So next is JR is dx, capital X, R with respect to 0, dq. Maybe I'll just write it down, 0 dx, dxr0 dy, dxr0 d phi, dyr0 dx, dyr0 dy, dyr0 d phi, and that comes out to be 1, 0, 0.5 L sine phi, 0, 1 minus 0.5 L cosine phi. So how do I get this? Well, I need to substitute dx, xr and yr, which came from here, xr, yr. So follow a similar procedure as jp to compute jr. Okay, so let's see where we are. We were trying to compute qj. We've computed jp and jr, but we still need to compute fp and fr. Fp and fr are the forces at p and r, but in frames 0. Okay. U1, U2, P, R, frame 1. Okay, let's compute fp0. You can see that this is again, from a previous lecture. You can use the homogeneous matrix, part of homogeneous matrix, the R, multiply it with fp in frame 1 to get the force in frame 0. So R10 is something which we know it's cosine phi, sine phi, sine phi, and cosine phi. What's fp1? It's the force in frame 1, right? So the force on frame 1 is, well, there's u2 along the y1 axis, and then there's nothing in the x1 axis. So 0 for the x1 and u2 for y1. This is the force in frame 1. Okay, so doing the math on this gives you minus u1 sine phi u1 cosine phi. Then we have fr0 is r10 fr in frame 1. We'll apply the same logic as before. We have force at r. The only force acting is u1. It's acting in the y1 direction. So the x force is 0. The y force is u1. And doing the math here gives me minus u2 sine phi u2 cosine phi. Okay, so now I need to put everything together. All this was trying to compute the generalized force capital Qj. So that's what I'm going to do right next. Okay. So here is the expression for capital Qj. It's Jp transpose Fp0 plus Jr transpose Fr0. I'm just going to put all the things down we wrote down so far. So we computed Jp, but Jp transpose is the transpose of Jp. So we'll write it as so 0, 1, 1, 0 minus L divided by 2 sine phi, 0, 1, L divided by 2 cosine phi. So this was minus u1 I need to check this. This is right. One zero minus 0.5. And then the force was, oh, this should be, my bad, this should be 2. This should be 1. So I need to put this force there. One, 0, to cosine phi, u1 sine phi minus u2, sorry, minus u1 sine phi space is minus u1 sine phi u2 cosine phi. u1 cosine phi. Okay. Okay, so what we get from this is something like this: u1 plus u2 sine phi, u1 plus u2 cosine phi, and then u1 minus u2 times 0.5 L. So these two are forces in x, y, and this one is moment in phi direction. Okay, if you think of statics, you can see that if you have thrust forces in the direction I've shown, then you can resolve it along the x and y direction to get these forces. And if you take the moment about center point, then you'll see it's simply u1 minus u2 0.5 L. And check u1, u2. Yeah, I think you'll get this. There's a minus sign I missed here. u2, put a minus sign here. Yeah, the fourth and final step is probably the easiest one, Euler-Lagrange equations. Okay, what is the Euler-Lagrange equations? Well, it is d dt dl dq dot minus dl dq j equals capital Qj, where L is something we wrote down earlier. It was right here. And this is T, this is V. I'm just going to sub that in. 0.5 m x dot square plus y dot square plus 0.5 I phi dot square. That's the kinetic energy minus mgy. So let's write the equations. Okay, the first one, d dt of Qj is, so Qj is x. So we have d dt dl dx dot minus dl dx equals q1. So this comes out to be d dt. So the derivative of L with respect to x dot. So it is only one term involving x dot. So it will be mx dot minus, there's no term in x, so that will be 0. And q1 is nothing but what we found here. So it's going to be minus u1 plus u2 sine phi. Okay, so we are almost there with the first equation. Let's take the derivative of this. Mx double dot equals minus u1 plus u2 sine phi, or x double dot equals minus u1 plus u2 sine phi by m. That's question 1. Okay, next we put qj equals y. Note that L is 0.5 m x dot square plus y dot square plus 0.5 I phi dot square minus mgy. So we'll need that now. T dt of dl dy dot minus t L dy equals q2. So d dt. Okay, we need to take the derivative of this thing with respect to y dot and see that as one term involving y dot, pm y dot minus dl dy. There's one term here with y, so minus mg equals q2. That q2 will come from this equation, the second one, u1 plus u2 cosine phi. Okay, so that gives me the second equation, which is going to be y double dot equals u1 plus u2 cosine phi divided by m. You're almost there. The third one is qj equals phi. So d dt dl d phi dot minus dl d phi equals q3. Okay. Okay, let's compute the derivative with respect to phi dot. So it will be only this term which is a phi dot. So I phi dot minus, there's no phi appearing in this, so it'll be 0. And q3 is what appears here, minus u1 minus u2 0.5L. So let's write it as minus u1 minus u2 0.5L. Okay, so the last equation is phi dot equals minus u1 minus u2 0.5L divided by I. Phi double dot. Okay, so those are my equations. This is equation 1, equation 2, and then equation 3. So it's pretty simple equations in 2D. If time permits, we'll do this in 3D, where the equations are more complex, and you can't solve them by hand like the way we've solved for a 2D bicopter. So what is done normally is we'll assume that this is similar to something we've done for the differential drive car. We'll assume that u1 plus u2 is u sum, and we'll take actually u2 minus u1 is ud difference. This is just to simplify. So once you have US UD, you can then revert back to U1 and U2, which are actually acting on the bicopter. So I'll write down the equations and we'll take a break. So the equations. Okay, so the bicopter equations are as follows. X double dot equals minus US divided by M sine of phi. Phi double dot is US divided by M. Sorry, I'm missing something. Yeah, I'm missing something. I forgot the mg completely. If the mg moves, the other side will be minus mg. So when you divide it by m, you'll get g. So I'm missing that term. Sorry about that. Okay, so we write this as plus minus g. And then finally, P double dot equals 0.5 L divided by I times UD, where US is U1 plus U2, UD is U2 minus U1. Okay. Now with that, here's some things to note. We want to eventually use these, and this is what we'll do today, is how to use these equations to control the bicopter. Now what you see is there are two controls. Either you can enlist them as U1 and U2, or US and UD. Like one of them would be US is sum of the two and UD is the difference. But there are three state variables: X, Y, and phi. Okay, so just like the pendulum we talked about, the double pendulum, we had two joints, one actuator. That system was called underactuated. This system is also underactuated. So two controls is less than three states. So system is underactuated. Okay, so it's kind of harder to control such systems because you don't have total control over all the 3 degrees of freedom using the same number of controls. Okay, so what we can do next is let's get some intuition about what's going on here. First of all, so some intuition. Okay, let's look. So with this equations, let's look at the case when phi is 0. Okay, so when we put phi equals 0, we see that x double dot equals 0. So I'm just going off the equations. Y double dot equals, so I just put phi equals 0 here. Cosine 0 is 1, so U S divided by M minus G. Right? For the bicopter to be, or the bicopter to hover, Y double dot should be 0. That it shouldn't be moving in the up direction. So we have the condition that US should be mg, right? When US, the thrust force, the sum of the forces is equal to mg, it says that the bicopter will remain stably hovering. What it means is, in this configuration, so here phi is equal to 0. The thrust force should be equal to mg. Here, the thrust force, which is upward, balances the weight due to gravity, and the bicopter will remain stable. Okay, so that's what you will expect in default conditions. It will not fall down if you do this. So what it means is that for the bicopter is you need to keep spinning the motors in order to be balanced due to gravity. Okay, so there's a cost of standing or hovering in the air, and that's why you'll see that these quadcopters have a charge time of like 15-20 minutes. Because of this reason, they cannot float in the air by themselves without using any power source. You know, if you have design for wings, it's possible that the wings, because of the design, they are able to generate a thrust force, and so they can basically make up for gravity without uh, without spinning anything, and that's why fixed wings, or not by fixed wings I mean literally wings, whichever large surface area can actually bear the weight of the plane. Okay, so this is one of the disadvantages. Now let's look at another condition. Let's turn the copter over. Second, let's consider what happens when phi equals 90 degrees. Okay, so I'll write the equations here because they moved to the previous page. The equations we wrote down was x dot equals us divided by m sine phi with a negative sign. Y double dot equals us divided by m cosine phi minus g, and then phi double dot equals 0.5 L ud divided by I. Just copy paste it. Okay, let me put now phi equals 90, so we have x double dot equals minus u divided by m times sine of 90 is 1. Y double dot equals cosine of 90 is 0, so it's minus g. So if you put us equals mg, right, that's the hovering condition, you'll see that x double dot will be equal to minus g and y double dot equals minus g. So this thing, this quadcopter is going to it's going to be turned now, so it's this way. Okay, so if you want to keep here, well, if you want to keep, well, if you put us equal to mg, then x double dot will not be equal to 0. But if you put us equal to 0, so if you want to prevent x double dot from it accelerating in the x double dot direction, you put x double 0, which means that us should be 0. So this condition ensures that it's not moving in the x double dot direction. But look at y double dot. You have no control over y double dot. Y double dot is simply minus g. So no matter what, you really can't do anything about the quadcopter just going down. You cannot control the system. The system is uncontrollable in this configuration. Quadcopter is uncontrollable when phi equals 90 degrees. So you just don't want the quadcopter to be in 90 degrees position because you just cannot control it. You always want to keep it upright. Okay, now there's a third case. So we've looked at the case when phi is 0, phi equals 90. But then there's an interesting case. What if phi is between 0 and pi divided by 2? And then we'll see minus also. So let's take this. Let's take phi is some number, let's say 0.1, okay, very close to 0. Okay, so here, if we put x double dot equals minus us m. Now, of course, a sign of phi, where phi is close to 0, is approximately minus us phi divided by m, right? Because phi is a small angle approximation. And then y double dot will be us divided by m cosine phi minus g. This will be similar to us m. Cosine of 0 is almost 1 minus g, right? Because phi is close to, because cosine phi is very close to 1 when phi is small, or phi is close to 0. Okay, so what we see here is these conditions, and what we want to do is, clearly we want to have keep y dot close to 0. So we'll set up us equals mg, which will basically ensure that when you put us equals mg, y double dot is 0. But when you put that in this equation, the first equation, minus mg m phi, you'll see that it's equal to minus g phi. Okay, which means that the quadcopter is going to accelerate towards the left. So the quadcopter, and I'll show all these things in simulation to you. So the quadcopter will, if you tilt it a little bit, my bad, tilt it a little bit, like so, p equal to 0.1, it will tend to move towards the left because of this term, moves left. Okay, similarly, if you consider the other case, p is minus pi by 2, 0, then you'll see that x double dot will be equal to g times phi, y double dot will be 0 when us equals mg. And then you'll see for a small tilt the other way, it says close to minus 0.1, you'll see that it actually is moves to the right. Okay, so slight tilt, and it just zoom past to the left or zoom past to the right. In fact, this strategy is actually used to control the bicopter. What you want to do is the following. So this is how control works for intuitive control of quadcopter. Oh, sorry, bicopter. Yes, so first, if you want to hover, just make us equal to mg, it will hover, and phi is close to 0. If you want it to move left, okay, like this, you need to keep us close to mg and use ud to change p to greater than 0. So when you use ud, because phi double dot is ud 0.5 L divided by I, commanding ud has a direct effect on phi. So if you increase ud, phi will change, which means that phi can be made positive or negative. But the moment you change phi, this is greater than 0, it'll start accelerating towards the left, as we've seen previously. When phi was close to 0.1, you saw that it accelerates to the left. Okay, so that's how you can move to the left. If you want to move to the right, you keep us close to mg, use ud to change phi to be less than 0, remembering that phi dot is ud 0.5 L divided by I. You can use ud to change phi dot, and so this will basically cause the quadcopter to move to the right. Phi is less than 0. Okay, if you want to go up or down, what will you do? Well, hovering is just us equals mg. So if you put a thrust force slightly greater than mg, you'll start going up. If you put a thrust force slightly less than mg, you'll go down. So go up, down, what you do is keep it vertical. So phi equal to 0. Us is slightly greater than mg, it goes up. If you put us slightly less than mg, it goes down. So this is how, this basically is all you need to get the quadcopter to move up, down, left, right. Okay, so moment it moves left, you can see it's tilted. Once you know where it lands in the position you want it to land, you quickly turn it back to 0 position, it'll stay put. And then you go back, keep it, you can basically control it that way. So what I did was I took the equations which we derived, I put it in a Python code, and now we can actually play with these controls to see if it's doing what we think it should do based on reasoning over the equations. So let me open my code, and then we can play with the code. So this is, well, first of all, I actually derived the equations using Python symbolic package, so you don't have to do it by hand. So if you run the code, it should spit out the equations, thinking, but here are the equations. This is the first equation. You can see minus u1 minus u2 sine phi, u1 plus u2 cosine phi. And then what is this? Let me see, what is this? This is, okay, just relate it to the code back here. Let's see. Okay, so I'm solving for the first x double dot y double dot phi dot. So it's basically giving me those three things. Here is the last equation. Here is the second to last. This is y double dot. This is the x double dot equation. I think I'm printing something else there previously. Let me see if I have printf. So I was printing the thrust force. I should just put. Yeah, this was the thrust force. The first three are the thrust forces, which is a line here. So the thrust forces are u1 minus u2 sine phi, u1 plus u2 cos phi, and the torque is 0.5 L u1 minus u2. And then the three equations are there. I wonder if you can do a line break by doing this. Okay, this might just give me the line break I need. Yeah, so now there's a line break here. So the first three are the equations, and for the forces, and the last are the equations of motion. So that's, once you get the equations, I have written some code, which is, it's a bit long, but a bulk of the code, so line 188 all the way to sorry, animate. I'm just trying to see how big my animation code is. So the animation code starts at 22, goes all the way to 100. So half of the code is animation, and the animation is long because I have shown, let me just play it. Okay, so I basically have shown the base of the quadcopter, the axles, and then the propellers. So all those things takes a bit of coding. Okay, but what goes into the code is some parameters. So those parameters are here. Mass is 1, inertia is 0.1, gravity 9.8, length is 0.2, and so on. The animation routine, which I will not discuss. The controller, we can change US and UD the way we want. The right-hand side for the bicopter, these are the equations which I wrote down. And then what we can do is we can set up the initial conditions here. So velocity in x, velocity in y phi dot. So what I did initially was I just set US equals m times g. Okay, device. Okay, that's a separate issue. We'll get to that in a bit. So US equals mg. So when you know US is mg and phi is 0, it will just stay put, and that's what you see. It's hovering. It's nothing is interesting is going on. The moment I increase this to something greater than mg, so 1.01 mg, you see it's taking off because thrust force is greater than gravity. If you do 0.99 mg, goes down. So let's keep it put and change phi now. So it starts, instead of having a phi of 0, let me put 0.1. Okay, so the hunch is that if you go 0.1, if you tilt it slightly, it start accelerating towards your left. You see it goes to the left. And then if you do it the other way, it goes to the right. Okay, so with those things, you can actually intuitively build a controller. You don't really need any fancy control theory. Just that those observations, going up, going down, left and right, you You can combine them in smart ways to make it go left, right, up and down. So there's a question: how do you control a device using this? Well, in a device, you can only control the thrust. You can control the speed of the motors. The speed of the motors is coupled with the thrust force, and you need to identify how the speed of the motors relates to the thrust force. And you can do simple experiments like, what you'll do is you'll keep the quadcopter in the air, you'll spin the motors, and you'll identify what thrust it generates. And once you have that thrust, you can find a mapping between the thrust force and the propeller speed. And you have basically identified the thrust force. Once you know the thrust force, then it's a matter of taking the simulation and going with this, because all the simulation cares about is just the thrust force. Once you have a measure for the thrust force on the device, you have it. But there's no real thrust force on a device. It's only motors spinning fast, but the spinning generates an upward force. The other thing I wanted to do with this code was to show you that you can actually do more than just moving left, right, up, and down. I'm going to try to get this to trace the figure 8, the lemniscate, or the infinity symbol. Okay, and for that, what I'll do is I will use partial feedback linearization, a technique we've seen before. So partial feedback linearization was used to control a manipulator, but it was a fully actuated system. So I'm going to basically use this to control an under-actuated system. And this is basically a smart way of setting up the control code so it will track the curve you care about. So feedback linearization to track a trajectory. So what you do is you set phi ref. Okay, so what's going on here is, first of all, there is a trajectory. And I'm interested in the lemniscate, right? This has a certain x ref, y ref, x dot ref, y dot ref, x double dot ref, y double dot ref, indicating the reference for the x and y position. Okay, now I don't care about the orientation of the drone. Okay, that is a free variable. It doesn't have to be at a specific location. So the way feedback linearization is set for this problem is you set phi ref as minus 1 divided by g x double dot ref plus k p, I call it kpx, x ref minus x plus kd x dot ref minus x dot. Okay, so that is phi ref. Okay, so phi ref is made a function of x ref. Okay, it's just something we've never seen before. Okay, and I won't delve into the derivation and all that, but this is what works for an actuated system. So then you have the U control is mg plus delta US. So it's split in two parts. There's a hovering part, which is mg, and then there is the part delta US, which actually gets it to track. And the delta US is equal to m times y double dot ref plus kpy y ref minus y plus kdy y dot ref minus y dot. Okay, so then that's how you control the thrust force, the sum of thrust forces. And then there is a third piece, which is ud, which is delta ud. So the why have I written it this way? There is no nominal part, like mg is a nominal part to keep it hovering. There's no nominal part for the difference. So I just wrote it as 0 plus ud, and then I just ignored the 0. So the delta ud is minus kd phi dot minus kp phi ref minus phi. Okay, the phi ref is defined here, and then phi is the angle of the base of the bicopter. Okay, so that's it. So we need to program two things. One is us and ud, but ud is delta ud, us is mg plus delta us, which comes from here. This in turns basically is a function of the x ref, y ref, and its derivatives. Okay, so let's see what this controller does in tracking. Yeah, so you can see that it's wobbling around, but it has to change its orientation, because unless it changes orientation, it cannot go to the right or left. And that is something you do not have to tune intuitively. It's taken care of by the controller. This is just showing the thrust, difference, sum, and then the trajectory. So I'll run this again. So turn left, it goes to the left, turn right, it turns to the right, and then it just uses that to move. It's basically taking the same ideas I had earlier, but putting them in an equation form, and then it takes care of all those things. So this code is it's a bit long, but 100 lines is just the animation. The key here is I need the reference motion, the figure 8, which comes from a curve. That curve is if you go and search for lemniscate parametric equation, I just took that curve, took the first derivative, second derivative, and that's how I got x dot ref, x double dot ref, and so on. The controller is, there should be a function called controller. That's it, controller. So this is the right hand side. I get us ud, because those are my inputs. They are implemented here, but then the controller itself is right here. So this is the same equations I wrote down on paper. I just have them put them here, and I chose some kp kd, the user chosen gains. Okay.
You said you looked up the parametric equation.
Yes. Yeah. No, you're no. So you're not supposed to. Square is harder to control. Well, square is not smooth. It has kinks. Yeah. So it will cause problems to be represented with a smooth curve. So all those curves have a property that the first and second derivative is continuous. For a square, it's unfortunately not continuous. But square is easy to do, because what you'll do is you just tilt the bicopter, you go left, you'll tilt back to 0, then reduce the thrust, you'll go down, and it's sort of easy to do it without all this.